Traditional shoemakers are a famously guarded group. In historical workshops, master craftsmen worked side by side, but they separated themselves with heavy canvas curtains to keep their personal techniques hidden from the bench next door. The greatest mysteries of the trade, however, were never kept in the cobbler's hands. They were engineered directly into the steel and wood of the tools themselves. A cobbler's bench is essentially a living museum. When you look closely at this vast array of hyper-specialized equipment, it becomes a forensic archaeological site waiting to be excavated. By reverse engineering these specific artifacts, we can uncover forgotten solutions to intense physical problems. To truly understand the craft, we have to look past the finished shoe and track the specific mechanical solutions contained in the steel and wood of the tool chest. Shaping flat, wet leather over a narrow wooden last requires immense physical force. The material is stubborn and deeply resistant to taking a new shape. Modern clamps aren't enough to stabilize this work. Cobblers use an ancient stirrup belt wrapped around their legs and under their feet. By leaning back, their own body weight acts as a mechanical counterweight, locking the shoe firmly in place so both hands remain completely free. Those free hands reach for the George Barnsley Bulldog pliers. These heavy steel jaws are designed to pull and wrap the leather tightly around the narrow waist of a boot, while the bottom handle physically straddles the wooden last to anchor the leverage. Its geometry serves a dual purpose. The top beak pinches leather into precise pleats, while a circular anvil sits below. The maker pulls the leather, then instantly flips the tool 180 degrees to drive a temporary nail home. The puller seamlessly becomes the hammer. These instruments are often passed down through generations, building a physical history. One surviving pair of Barnsley pliers originally belonged to Francesco Berluti, the private bootmaker for Benito Mussolini. When a modern craftsman grips those exact inherited pliers, they employ the same physical leverage and muscle memory, perfected by their predecessors a century ago. The temporary nails used during that lasting sequence follow very strict parameters. They must measure exactly 30 millimeters long and 1.2 millimeters thick to protect the maker's fingers. But more importantly, they must be copper-coated. If a cobbler uses plain steel fasteners on wet, vegetable-tanned leather, a rapid chemical reaction occurs. The steel interacts with the tannins in the hide, leaving permanent, destructive black stains. Because speed was vital, historical cobblers kept a handful of these tacks directly in their mouths. That is why vintage boxes of shoe tacks proudly printed the word sterilized on the label. If a maker accidentally pricked their finger or lip, that sterile packaging was the only defense against a work-stopping infection. Beyond chemistry, the tools also solved strict spatial limits. Consider the rigid shaft of a tall writing boot. There is zero clearance to swing a standard hammer down into that dark, inaccessible toe. The solution is the internal slide hammer. The maker loads a spiral shaft nail into the side hole of the tool, lowers it deep into the boot, and drops the sliding weight. One heavy vertical strike forcefully sets the nail into the heel block. Cobblers successfully navigated chemical corrosion and spatial constraints, solving industrial-scale problems at a single wooden bench. This engineering extends past heavy metals into the organic materials holding the shoe together. A cobbler begins a stitch by deconstructing 5 separate strands of natural linen, carefully rasping the ends to thin them out into delicate points. Raw linen lacks natural protection. To seal it, the maker applies a sticky shoemaker's resin. By rapidly rubbing the wax up and down the thread under high tension, the resulting friction generates enough heat to melt and infuse the resin deep into the fibers. You cannot thread this through a standard metal needle. Rigid steel needles simply cannot navigate the sharply curved channels, or holdfasts, carved directly into the leather insole. Instead, they rely on a biological alternative. The maker twists flexible, natural wild boar bristles onto the thinned ends of the linen. This biological bristle acts as a highly pliable needle, bending fluidly through the tight leather curves without snapping. Once threaded, the stitch is pulled tight with immense physical force. The pressure causes the friction wax to heat up and melt slightly, permanently welding the hole shut. This self-sealing thermodynamic bond is a feat of organic engineering that modern synthetic machines still struggle to replicate today. When you pull back from the microscopic details, you see a fully constructed, hand-welted shoe resting quietly beside the exact tools that forged it. The Bulldog pliers, the copper nails, and the boar bristles remain functional necessities that automation cannot easily duplicate. Their value lies in their design. The geometry of these tools physically forces the maker to adopt traditional muscle memory, guiding human hands through centuries of specialized problem-solving. By maintaining these specific instruments, master craftsmen ensure that the boots they build and the specialized knowledge required to make them continue into the next century.